So for me, this says that look, since we don't know any of these values, one should really, think about finding axions wherever possible instead of making, bad theory arguments for why one is better than the other.
Sorry, what is the I subscript on A?
The initial value of A.
Oh, initial.
Sorry. And there are some very good constraints on axions. All the physics of the axion determines on one single parameter, Fa, the scale where the symmetry is broken. Okay. If F is much below 10 to the 9 GeV, it's already ruled out. In fact, it couples too strongly to the standard model. There are a variety of astrophysical bounds, etc. on this stuff. If F is above 10 to the 11 GeV, that's really where the axion can be all of the dark matter. Anywhere above that is possible. For a narrow range of parameters of F of around 10 to the 12 GeV, there is a very good way to search for axions, and you've probably heard of this before, and that's the so-called microwave cavity or the SQUID cavity experiments. They now go with a fancy title of ADMX. And what these experiments are based on is that the axion couples to electromagnetism also. It can have this coupling. It doesn't have to, but in most models it will, of the form A over F, FF dual. Okay? And when this coupling exists, what happens is that if you have a region of a background magnetic field, the dark matter axion can come in and convert to a photon. Okay? And then you try to detect that very small electromagnetic energy being deposited. And these experiments are very good, but it's very, very hard for them to go very much beyond this particular range where they're operating right now, F of about 10 to the 12. And there's this big parameter space about that. So how do you get there? It's very, very hard to make these experiments change this value of F where they operate at for two fundamental reasons. The first of which is that these experiments are looking for the conversion of an axion to a photon. So fundamentally, they're looking for a cross-section. Now, every interaction of the axion goes as 1 over Fa. So when you go from the matrix element to a cross-section, you get hit by 1 over F squared, right? The matrix element squared. So as F becomes larger, you're paying a suppression in the conversion. There's, however, an even more fundamental problem, and that is actually intrinsic to this operator itself. So the point is that the operator A over FF dual, right? When A is a dead constant in space, say there's no dynamics to A at all, then FF dual is just a pure derivative in electromagnetism. It does not give rise to any physical effects. So all physical effects of this operator have to be proportional to a derivative acting on the axion field. Okay? And when a derivative hits the axion field, you bring in an additional length scale, which is the mass of the axion, the problem, or the axion wavelength. So something else has to swallow up that extra length scale, and what swallows up that extra length scale is the size of your experiment. Right? So secretly, this operator always contains a suppression, which is the size of the experiment over the axion wavelength. Okay? Now, as F becomes very, very large, right, the axion wavelength gets very, very big, which means that this conversion efficiency gets very, very suppressed. So when F is of around 10 to the 12 GeV, it turns out that the axion wavelength is order like, a few centimeters. So you can build like a centimeter-sized cavity, and then you can sort of convert efficiently. But as F becomes larger, say F becomes 10 to the 16 GeV, the wavelength gets to be about a kilometer. And if your cavity is still 1 centimeter in size, you take a big hit. Okay? So for these two fundamental reasons, these experiments are going to have an incredibly hard time going very much beyond where they are. Okay. Oh, so here the axion is not even quite dark matter, right? So that's a different story altogether. So one can think about axion helioscopes, possibly force measurements, things like that. But that's a different ball. So this raises an interesting question. Since the axion can be dark matter anywhere above this, how do you ever go to high F axions? So here is a different proposal. Okay, the axion, in addition to coupling to electromagnetism, it has to couple the gluons. The QCD axion has to couple the gluons. That is what makes it the QCD axion. Right? This is the defining coupling of the axion. Let's think about what this operator does. Right? So the strong CP problem is the observation that when there's a constant value of theta, you nevertheless get a nucleon EDN that is order 10 to the minus 16 times theta. And that happens because of instanton effects in QCD, non-perturbative stuff. Similarly, when there's the axion as dark matter, there's a non-zero value for the axion field locally, right? That's how the axion is dark matter. There's a non-zero value of that field. And that means you're going to give rise to a nucleon electric dipole moment that is order 10 to the minus 16 times A over F. Okay? They're identical physics, that's the same thing. How big is that value? Let's just make an estimate. Okay. So to do that, we need to know the amplitude of the axion field. And that you can do by simply stating that m squared A squared, which is the energy density in dark matter, locally, is equal to the energy density of dark matter, since I'm assuming that axion is a dark matter. Okay. So I do that, I find A over F. Okay. And A over F turns out to be a value which is 3 times 10 to the minus 19 and is independent of Fa. It doesn't matter what the value of Fa is. Why is it independent of Fa? Well, the reason is because of the fact that when I compute A over F, right, I have to divide it by the axion mass, and the axion mass goes as lambda QCD squared over Fa roughly. Okay? So the F's essentially cancel out. Right? So this is very interesting. If you had some way in which you can measure this very, very small value of the EDM, right, you suddenly become sensitive to a wide variety of axions, wide varieties of FAs. Why is that? It's for two reasons. The first of which is that I am measuring the matrix element here directly, right? And EDM directly measures the matrix element. And that's better than the cross section, so that is one win. The second equally important win is that this effect of the axion is a non-derivative effect, right? The axion field can be dead constant, but because of QCD, I nevertheless get a non-zero EDM. Okay? So I'm no longer suppressed by effects of the axion wavelength. So there's a big difference between this approach and looking for the coupling to electromagnetism. Right? I'm making use of the non-perturbative effect of QCD directly. Okay? This, however, is an incredibly small value of the dipole moment. It's about 9 orders of magnitude smaller than the present bound on the EDM. Okay? How is there even ever a hope of seeing this? There's, however, a very, very big difference between this EDM, this electric dipole moment, and standard searches for EDMs. Right? In a standard search for electric dipole moment, you're looking for a time-independent value of the electric dipole moment. But the axion-induced value of the EDM is not time-independent. In fact, it oscillates back and forth. Why does it oscillate back and forth? Because the axion field, when it's dark matter, the way it is the dark matter is because it's oscillating back and forth. Right? That's how it is dark matter. And what frequency is it oscillating at? It's oscillating at the frequency that is equal to the mass of the axion, which if the PQ breaking scale is about the gut scale, about 10 to the 16 GeV, that's about a megahertz oscillation. Okay? So the axion-induced EDM is essentially a time-varying EDM that's oscillating at something like a laboratory frequency. Okay? Very, very different from what you are conventionally searching for in a static EDM search. And we're going to make use of that time variation in a very fundamental way to go search for this.
Sorry, when you actually do experiments, I would think you're still looking at some cross-section type of stuff.
No.
No. So it's because of interference, so you see
basically.
the indirect.
Yeah. So I mean, the way you often look for a dipole moment is through a spin-precession experiment, and that is roughly the interference of spin up and spin down. That's one way to think about it. Exactly. So here's a simple setup. Okay. Let's say you take a sample of material and you align all the spins in one direction by the application of an external magnetic field. Let's say you do that. Let's apply an electric field perpendicular to that direction. Now, if there is no axion and there is no EDM, then these spins will just stay as is, right? Like nothing happens. I've got a magnetic dipole, that's a nucleus spin there, and there's an electric dipole, electric field perpendicular, like nothing happens. However, if there's an EDM over here, if there's an electric dipole moment, now you've got an electric dipole moment that is perpendicular to an applied electric field. Okay? So much like how a magnetic dipole perpendicular to a magnetic field will precess, an electric dipole moment perpendicular to electric field will also start precessing. So when that is the case, the spins will slowly start precessing. Okay? As they precess, they will change the magnetization of the material, because each spin here carries its own nuclear magnetic moment, so all of those magnetic fields will change, and there will be a change to the magnetization of the material. Okay? And that is something that you can measure with the SQUID, which is a very, very precise magnetometer. Okay? So that's the basic idea. So let's now talk about details of this, right? After the rest of my talk, I will tell you how big the signal is, how do you compute how big the signal is, and talk about the parameters, what kind of materials do you need to go off these numbers, talk about sensitivities, and then finally conclude. Signal? Okay, so how big is the angle? Okay, how big is the magnetic field? So to measure the magnetic field, let's first talk about how big the precession angle is. Okay, how big is that precession angle? That precession angle is given by this formula, and it's proportional to the dipole moment times electric field. Not very surprising. It's then got all of these sinusoidal factors. Where do these sinusoidal factors come from? Okay, so the point is, with an external magnetic field applied to the system, right? There's a natural axis at which you can quantize the spins. The spins can be quantized to the left or to the right. And the two of them have an energy difference, which is mu b and minus mu b, right? So there's a natural, if you will, Larmor precession frequency of the system set by the external magnetic field. Okay? And what you have is a time-dependent perturbation, right? The dipole moment of the axion is oscillating back and forth. And when that oscillation frequency equals the frequency of the Laurent precession frequency, there's going to be a resonant response to the system. Okay, and that's exactly what's going on here. Okay, when the axion mass is equal to the Laurent precession frequency, the system has a big resonance, and the signal will build up linearly in time when these two parameters are small. Okay, and of course it all oscillates fundamentally at the Laurent precession frequency. Okay, so the technical term for this is that what's happening in the system is that there's sort of resonant Rabi oscillations. It's a two-state system. There's a perturbation. There's a time-dependent perturbation, and when the frequencies match, you get a big response. Okay, and how big is the magnetic field? Well, the change in the magnetic field is then the angle delta theta that we computed in the previous slide times the number density of nuclear spins times the nuclear Bohr magneton. Okay? And of course, we don't actually know the value of the axion mass. So the way this experiment would work is that you would operate at some value of the B field to start with, some magnetic field, and then you slowly change the external magnetic field, and then you try to find one point where there's a resonance. That's how it works. Let's do a rough estimate of numbers. How big are we talking about? So this is the slide from the formula from the previous slide. Pretty much everything is the same, except I stuck in a factor of t here, and that's like a polarization fraction, right? Because maybe you don't polarize all the nuclei. How well do you do? So these three numbers are more or less fixed in stone. If you take a solid, that the number density is about 10 to the 22 per centimeter cube. The nuclear Bohr magneton is E over GeV, and the local dark matter density gives you an EDM that is order 10 to the minus 34 centimeters. Can't do much about those numbers. The remaining numbers we can be kind of clever. Okay, so let's assume that the polarization fraction is order 1. Let's say we do that. Okay, and I have to put in some electric field over here. Let's say that's a pretty large field, like 10 to the 6 volts per centimeter. Okay, it's pretty large. We'll talk about how we get those fields. Finally, there's a third parameter, which is that this resonance keeps getting bigger and bigger as the time gets larger and larger. Right? Now something could cut that off, something in the material, something in the dark matter, but for now let's just assume that we can do this for about a second. So for a full second we can gain the precession of the thing. Okay. What do we get? Multiplying those numbers, the magnetic field is about 10 to the minus 2 femtotelta. Okay. And that's a magnetic field that is very, very close to being measured. I mean, it can be measured with modern magnetometers. It's not too difficult to do that. Okay. So you can see that already the numbers seem to be going in a direction where this is not impossible, where this is feasible. But how do we get these parameters? Right? So let's talk about that.
Can you translate femto into English? I forget what that is.
10 to the minus 15.
Thank you.
Okay. So nuclear polarization. Now I won't go into much details about how this is done. It's not easy, okay, but it's been demonstrated in a bunch of systems. The basic idea is that you first create some external magnetic field. It's a large field, like 10 Tesla. You cool this thing down to about 4 Kelvin, and once you do that, there are further things you need to do, like you've got to usually pump the system, blah, blah, blah. I mean, there's a bunch of technology that needs to happen, but, once you do all of that, you can basically keep the spins polarized for about 3 hours. I'm happy to talk to you in more detail about this, but this is not, this is difficult, but not impossible, okay? And it's been demonstrated to better than 90% in liquid xenon, diamond, a bunch of things like that. Anyway, that's definitely hard, but not impossible. So, order 1 nuclear polarization seems reasonable. The second is effective electric field, and there's some real physics here. Okay, so what am I measuring, right? I'm measuring basically the value of the electric field at the position of the nucleus. That's what's giving rise to this coupling. But here's the problem, right? It goes by the name of Schiff's theorem, and it's the following observation. It says that this system is in equilibrium, right? When it's in equilibrium, the force at the position of the nucleus must vanish. Okay, but the nucleus is only acted upon by electrostatic forces, so the effective electric field at the position of the nucleus always needs to vanish. And what that means is the following, is that, there is some electric field, whatever. Let's say you apply some electric field in the system, right? The electrons in the system will rearrange themselves in such a manner as to cancel the electric field at the position of the nucleus, right? That's required by equilibrium. Okay. And of course, that would completely kill my story, because then there's no coupling between the dipole moment and the electric field. But as you know, this is a problem not just for a time-varying EDM, this is also a problem for a static EDM, right? Whether it varies in time or not, like this thing doesn't really care. And people do use neutral systems to search for EDMs all the time. What's the way out? The way out is that the nucleus is not a point object. Okay, it's got a finite size, and that means that higher order moments of the electric field. It's true the electric field itself vanishes, but its gradients don't, and the gradients can then couple to the nuclear charge distribution and give rise to a non-zero precession. Okay, and these effects typically scale like 10 to the minus 9 times Z cubed. Okay. So it's usually a big suppression, which is why people always use sort of high Z nuclei like lead or mercury, where Z is order 200, and that suppression becomes at 10 to the minus 3. Okay? So we would have to use a high Z nucleus material, much like people who search for electric dipole moments. So let's say we do that. But I already told you that I wanted a pretty large electric field, like 10 to the 6 volts per centimeter. And that has to exist on top of the suppression. Right? So how the hell am I going to get that? So the idea is that one can use what are called polar crystals. Okay? So polar crystals are crystals where the central atom in the system does not have an axis of symmetry. Okay? So an example of this is sort of lead titanate. Okay? The way you want to think about this is very much like, let's say you have a molecule, for example, and you apply an electric field, external electric field, the molecule will get polarized. So once the molecule has gotten polarized, there are very, very large internal atomic electric fields acting at the position of the nucleus. Right? And those fields can be incredibly large. And the trick is to use one of those sort of polar crystals, which have the same property, that since there is no axis of symmetry, much like a polarized molecule, internal fields can be very, very big. Okay? So what we would have to use is basically some kind of polar crystal that is, has lead and things like that. And a good example of this is sort of lead titanate. People are trying to use this for measuring the standard EDM, the solid state EDM, right? Precisely because of the fact that they also benefit from the large effective electric field. And in such systems, even after the shift suppression, it's actually pretty reasonable to get these large electric fields, 10 to the 6 volts per centimeter. Okay. So that's the proposal. We would need a system like lead titanate, some kind of polar crystal to do this. There's kind of a technical point, which is that if you're looking for a static EDM, the only way you will actually see it is by reversing the external electric field. Otherwise, you don't know what's happening, right? You're looking for for a static EDM and it doesn't change in time, the only way you know it's there is by reversing the electric field and then seeing if your signal flips back and forth. But for a time-dependent system, that's not required. A static electric field can also see it, right? And technically that means we don't quite need a ferroelectric. We could just use any of the polar crystals. And in such systems, larger electric fields may be possible, although we don't assume that. Okay, some more physics here, which is the interrogation time. Okay, and that's the question of how long do I have to linearly build up the value of the field, right? What cuts that off? Two things can cut it off. The first of which is that there is the axion field itself will stop being coherent after some time, right? There's after all some field of the galaxy. There's no reason why it will remain coherent forever. Second is some kind of property of the material itself. Okay, material limitations can prevent that. Let's talk about both of these. How large can T be? So here the point is the following, right? Imagine the axion field was dead constant in space. If it's dead constant in space, the field will just keep oscillating back and forth forever. I can wait until the cows come home to do this, right? However, in the universe, there's no reason why the field will remain constant throughout, right? There's after a certain value, there will be a gradient in the field, okay? And as the experiment, as a device goes from a region where there's one value of the field to another value of the field, you lose coherence, right? So you stop building the signal up linearly. So to estimate this, we need to first of all know what is the size of the spatial homogeneity of the field. That's pretty easy to do. This is just a classical field, right? And the regions of spatial homogeneity basically correspond to the de Broglie wavelength of the field, right? So once you're within one de Broglie wavelength, you're going to be more or less the same value, and you go from one region to another region of different de Broglie wavelength, your field value will change. Okay. How big is that spatial homogeneity? Well, it's mv. Okay, v is 10 to the minus 3, the velocity of dark matter in the galaxy. We don't care just about the spatial homogeneity. What we really care about is the time, right? Because that's the amount of time I have to do this. So how much time does the Earth take to go from one value of the field to another? Well, the relative velocity of the Earth with respect to the dark matter is also v, right? So the amount of time I have is then 1 over mv squared. Okay. And you can think about this simply as saying that, look, there is the axion field has just one value, the mass, that's the frequency at which it's oscillating. But in the galaxy, it's got some velocity, so the field value the power has sort of dissipated, okay, over a frequency range given by mv squared, the kinetic distribution. Okay. And here comes the point, which is that if f is about 10 to the 16 GeV, then the mass of the axion is light enough that the coherence time is about 1 second. Okay, and that's another very important point. So remember that the base value of the signal, which is the EDM itself, right, does not care about FA at all. Whatever the value of FA has got the same value of the dipole moment. But my ability to see it It depends upon how much time I have to see it. The larger this time is, the more the signal will build up, the easier it is for me to see it, right? And in this case, therefore, the higher the value of Fa, the easier it is for me to see it, because the field remains coherent for longer. Okay, so this is completely the opposite of the searches using photons, because there the larger the value of F, you're screwed in no time. Right? Here, the bigger the value of F, the better it is.
So how do we estimate this V here? It's just by assuming the expansion and look at what's the current temperature of the...
It's just the bit of loss of the galaxy.
Okay.
Right? We know how much mass there is in the galaxy. That gives you, GM over square root of GM over. All right. So the second issue is, so that's the axion field. The axion field will remain coherent as long as it's sufficiently light. The second issue is the material itself. Can something about the material itself prevent you from building this resonance forever? Okay. And here is the following problem. Each nuclear spin is just processing about its own local magnetic field, right? That sets the local value of the Larmor precision frequency that is going around. Now, what can happen is that the value of the magnetic field here may not be exactly the same as the value here. So when the two fields have slightly different Larmor precision frequencies, after some time they will start processing at different rates, right? And they no longer respond coherently to the full change. So you stop losing coherence. You start losing coherence. Okay. So essentially, local variations in the Larmor precision frequency leads to something dephasing, and that's called T2 because of these changes in the local value of the magnetic field. Naturally, in a solid, this T2 time scale is about a millisecond. Okay, much smaller than what I wanted. But thankfully, I'm talking about all of this, 70 years after NMR was first invented. And of course, this is a problem for anyone who wants to use nuclear magnetic resonance to do anything, because everybody benefits from having a larger coherence. So a lot of technology has been developed on ways to beat this, make it much longer. And they go by the term of what's called dynamic decoupling. Okay, and the basic idea in these for the dynamic decoupling is the following. Essentially, what you're doing is that the problem is this, right? Is that this one spin starts processing faster than the next guy. Okay. So the way these things work is that every now and then, every time, within one T2 time scale, you flip all the spins by 180 degrees. Okay. So suppose you do that. What does that do? Okay. Imagine all these spins are essentially sort of runners in a sort of going around a circle, right? And so the problem is some guys are faster than the others. So after some time, instead of all of them going at the same speed, some guys are way before the others. Okay. Let's say you swap everyone by 180 degrees. That means now you've pushed the slower guys to the top and the faster guys at the back. And the faster guys can then catch up with them. And then they all can move together. So it's sort of like socialism, right? Where you are punishing the winners, you promote the losers, and then the winners catch up with the losers again. So that's exactly the principle. It works very well in NMR. Okay, and that's been demonstrated now in a variety of systems. You've got in silicon, they've got about 40 seconds. A dramatic improvement over the 1 millisecond time scale, and a liquid xenon about 1300 seconds. So our experimentalist colleagues think that 1 second should not be a big problem. The technique should work just as well.
I'm trying to understand why it should be so much larger in xenon, or what is the effect here?
Oh, so there are two issues there. The first of which is that liquids typically have an extra kind of averaging. The problem is, the thing is, this spin is, doing something funny to this guy, right? But in a liquid, it won't remain in exactly the same position. It'll start moving around. And that creates a motional averaging, which makes it less of a problem. All right. So here is the brief recap, right? This is the formula that I had from the, one of the few slides earlier, the value of the magnetic field, and these are the numbers that I require. So, order 1 nuclear polarization seems possible. It requires some fancy techniques, but techniques that have been demonstrated. Large effective electric fields possible, okay, in these polar crystals, and one can indeed build the coherence linearly for about a second. Using a couple of things. The first of which would be techniques like dynamic decoupling, which make the NMR resonance stay resonant for a longer period of time, and the axion mass is sufficiently light. Okay. Now, I'll point out that each of these have been independently demonstrated in different systems, but nobody's actually put them all together because there was really no point to doing that before. Hopefully, this creates a point. And if you successfully manage to do all of this, you're looking at measuring magnetic fields of order 10 to the minus 2 femtotesla, which is not an incredibly difficult field to measure. So let's talk about sensitivities. Okay, how good are we at measuring these things? So let's talk about noise. That's what determines sensitivities. There are really three kinds of issues here. The first is the magnetization noise of the sample. So I put some sample there, right? Some material. That material itself will have time-varying magnetic fields. That will kind of screw with me. How big are they? Second is magnetometer noise. How small of a magnetic field can I really reasonably measure? And the final is the issue of integration time. Any noise can be beaten down if you wait for a sufficiently long period of time, but eventually you want to do something else with your life. So how much time do you really have? Okay, so magnetization noise, right? This is the fact that if I have a sample of material there, and I'm trying to measure the transverse magnetic field, there will be some random magnetic field from the sample itself. How big is that? The basic point here is that each spin will have some random initial transverse projection. I have all my spins polarized in one direction, but if you measure the transverse component, each of them quantum mechanically will have some transverse projection there, and that's just random. But that's okay. That is just some initial value of the transverse magnetic field. I don't care about that, right? I care that it actually has to vary at the lot more precision frequency for it to be noise for me. So I need it to be a time-varying source of noise. And that's of course been well studied because this is standard thing for NMR people. And let's look at how it actually scales. The first thing to notice is that because this is a random initial thing, right? The net value of the magnetic field will scale as the nuclear board magneton over R cube. That's just the value of the field from each spin, times the square root of the number density of spins. The square root of the number of spins, sorry. Right? That's how you add in quadrature. Okay? And that means that the value of this magnetization noise would go as square root of 1 over the volume. Right? This R cube comes here and here. So if you make a larger sample, the value of the magnetization noise goes down at the square root of the volume. Then there is, but that's of course the initial value itself, right? Next I need some time variation for it to be noise. Okay? And that's been studied by these guys and it's got this unpleasant looking formula like this. Let me just tell you what that formula actually means in the next slide. Okay? This is the value of the, by how much is each spin wobbling around? What's the time variation of each spin? Okay? So remember, notice that this thing is proportional to T2, right? When T2 is 0, this doesn't exist at all. Why does it depend upon T2? Well, T2 is that randomization. It's this time scale at which I'm losing transverse coherence, right? So the point is this, is that in the absence of anything random happening in the system, these spins will just precess at the normal precession frequency. That's the only frequency of the problem. And if I'm measuring something in a different frequency band, then I don't see anything at all, right? There's no noise. So something random needs to happen to move all the power in that frequency to a neighboring frequency bit. And the biggest source of randomness in the system is T2. So that's what is making the spins go off whack once in a while. Okay? And that's why this formula depends upon T2. And the rest of this is more or less just dimensional analysis. Once you know that, what does it do? Okay. So that's the magnetization noise. And we will plot this when I show you my final sensitivity. Okay. The next is the magnetometer. How small of a magnetic field can you really measure? So the point here is that the SQUID, right, that's a device if you've not heard of it before, it's some device that actually measures the magnetic flux. Okay? So if you take a sample that's got a fixed magnetic field and you make the sample bigger and bigger, then essentially you can capture more and more of that flux on a pickup loop, and you can sort of inductively couple that to a SQUID. So the larger the size of the sample, the more flux you can capture, and the smaller the magnetic field you can measure. Okay? So if you use a typical SQUID that people kind of have, one can measure a magnetic field as order of 0.1 times the square root of it. This is fairly standard. Okay? For assuming the sample size is about 10 centimeters. So it's a relatively big sample, but not insane. The final issue is the integration time. How much time do I really have to see the signal? Okay? And here let's look at how the signal to noise scales over different ranges. Okay? So for really, really short times, when much below the Axion Coherence time, as well as the T2, right, the time over which my system still remains resonant, during that time, the signal will build up linearly in time, right? I'm gaining the full resonance, so my signal goes up in time. Noise, of course, integrates down at square root of t, so signal to noise will go up as t to the 3/2. When you're looking at time scales that are longer than T2, okay, but below the Axion Coherence time, during this time, basically the size of the signal, okay, I've maxed out on my resonance. I can't gain any more on the resonance. So that's limited by T2, the most I can gain there. But the noise will still integrate down. Right? And that means my signal to noise would go up as square root of t. Smaller gain than t to the 3/2. The final time scale is when I'm looking at time scales much longer than the axion coherence time. Right? Over this time scale, the signal just looks like excess noise. Right? The axion field itself is noisy, it's changing a lot, and this just looks like noise. So the statistical question I'm asking is there more noise in one frequency bin relative to the one next to it? And if you do the statistics right, you basically realize that the signal to noise goes up as t to the 1/4. Okay? So we'll again fold all of these things in when I show you the sensitivity plot in the next slides. And what we've basically said is, we want to scan a full bandwidth of axions, right? So if you start with, say, 1 megahertz, we want to go from 1 megahertz to 10 megahertz, okay? And we want to scan this full frequency in about 3 years, since we don't know the axion mass. And that roughly means that in each frequency band, we spend about a few seconds, okay, before we make a decision on whether there's the axion there or not. And using that input, here's the projected sensitivity in my money plot, okay? So here is the mass of the axion in EV, the x-axis here, plotted in frequency at the top, okay? And in the y-axis is the coefficient of this operator, GD, okay? And basically this GD is the coefficient of the EDM, of the dipole moment, okay? GD times the axion and the nuclear EDM, okay? Okay? And for the axion dark matter, basically what you do is you take this value of GD and you multiply it by the value of the local axion amplitude, okay? The field value. And that gives you a dipole moment. And that gives a prediction for the QCD axion, because the QCD axion, there are no more parameters really, once you say all of it is the dark matter. And that is this purple line. Okay? These things, the blue filled area and the green filled area, those are all current bound. So all of this is ruled out for this coefficient GD. Everything below this is still viable parameter space. Okay? And these are two experiments that we are proposing, right? The first is a pretty simple experiment, with only 10 to the minus 3 nuclear polarization, very easy to do, nothing very fancy, but still assuming like a 10 centimeter cube volume, right? And T2s of about a second. That gives you this line, okay? So that of course does not get you to the QCD axion. We can only probe parameter space here, okay? However, if you go to this red line here, and that assumes that we get order 1 nuclear polarization. We can actually manage to make all this work and polarize all the nuclei. Then any region where the red line intersects the purple, and below that, all of this region, we can actually start probing right now. Okay. So the place where the two of them meet, roughly here, accidentally corresponds to about the gut scale, when FA is about 10 to the 16 GeV. And going to the left here, that's the higher Fs, right? Like Planck scale, things like that. Much easier.
What is the dark purple and the bright purple?
Good. Yeah, there are a couple more things to say actually. Thank you for reminding me. So this is what ADMX is right now. This is about 10 to the 12 GeV. And below that, the axion cannot be a dark matter. You need other ways of looking at it. This is about the Planck scale. People typically don't like that is larger than the Planck scale. Although different people have different opinions about this. But that's just where this purple line ends. This red dotted line is actually the magnetization noise that I talked about, the random flipping of spins in the material itself. And as you can see, that's subdominant to our magnetometer noise. Because this curve is currently drawn by assuming that the magnetic field I can see is about 0.1 Tesla per root meter. So if my magnetometers get better, I can still keep eating more and more of the signal until I get limited by the magnetization noise. So there's still quite a bit of things to be done as technology improves and the magnetometers get better and better. And there is this sharp vertical line here, right? It's very hard for us to go much beyond 10 to the 8 hertz here. And that is basically set by the fact that I'm looking at a resonance system. This is the NMR resonance. And the highest frequency I can resonate with is set by the largest magnetic field I can create in the lab. Because the resonant frequency goes as mu b, right? And if you take something like a 10 Tesla magnetic field, then I can't go to any frequency much higher than that, about 10 to the 8 hertz. I'll briefly mention this another operator, which is also I think very interesting. Axions can also couple to nucleons through this operator, d mu a over fa, psi bar gamma mu gamma phi psi. Okay, that's the axial nuclear moment roughly. And if you go to the non-relativistic limit, what that operator boils down to is this. Okay, a over f ma mass of the axion times the velocity of the axion dotted with spin. Okay, this is just the non-relativistic version of this. And what this means is the following: is that if I take a spin and I have some axion field flowing by you, like the wind of dark matter axions, for example, the spin will start precessing. Because this is very much like a background magnetic field now. Right? It's the same coupling. It's the same sort of effect. So one thing you can do is essentially take a system and let's say you polarize all the spins in some direction and place it perpendicular or roughly perpendicular to the velocity of the axions in the galaxy. That will then cause these spins to precess. And that will again change the magnetization of the material. You can use exactly the same kinds of techniques we talked about to measure them. The advantage of doing this is that one does not need a high Z nucleus. I'm not measuring the nuclear EDM, right? I'm just measuring some spin precession due to wind. And I can use any material like xenon or helium, things where all the techniques I've talked about earlier, like nuclear polarization, large T2, all of that is very, very easy to do and have been demonstrated. So you can easily take any of those systems and just sort of perform this technique and see if you see a spin resonance. Unfortunately, if you plot that, it doesn't quite get you to the QCD axion. Okay, so this is the same operator. I mean, the coefficient of the nuclear axial moment, d mu a psi bar gamma mu gamma phi psi. Okay, that's that parameter, and this is the mass in EV, and this is frequency in hertz. And the QCD axion, there's a prediction for what the value should be if it is all of the dark matter. And the red and the blue lines are our two different kinds of experiments, one for helium, the other for xenon. As you can see, it doesn't really quite get to the QCD axion. Okay. However, it can probe a lot of this parameter space up here because the previous coupling I talked about, this coupling, right? It can exist for any Goldstone boson. It doesn't have to be for the QCD axion. So any Goldstone boson you have will have this coupling. It could be dark matter. There's no particular reason why the QCD axion has to be the dark matter. So you can search for a variety of such Goldstone bosons like dark matter with that technique. And all of this is like open parameter space right now. You can easily get a big chunk there.
Okay, like an annual modulation for this.
So we actually don't even need annual modulation. So there is an annual modulation. You're absolutely right because there's velocity dependence. But the important thing here is the fact that the operator is proportional to the axion field directly, right? And the axion or the Goldstone boson field. So this field itself is oscillating back and forth, right? So it'll be oscillating back and forth at a megahertz frequency. So it's much easier to see than a very, very slow annual modulation. Because for an annual modulation, you wait for a full damn year, right? Here, the signal is modulating at 1 megahertz. So you just wait pretty quickly and see if it's really doing that. And in fact, like that brings up a pretty important point, which is that, how would you confirm a signal in an experiment like this, right? For Dharma or whatever, we've been talking about this for years, whether or not this is a real signal or not, right? So the important thing here is that since this is a very big field, a classical field, basically, the axion dark matter, you can, let's say, build one experiment at Stanford and one at Berkeley, right? And if the axion is really causing the dark matter, since the signal will remain coherent within the axion wavelength, right? And the axion wavelength is like kilometers, it's like easily 1,000 kilometers in these situations. So you can build one device at Stanford, the other at Berkeley, and you can cross-correlate, right? And the signal should do exactly the same in both the same place, in both institutions. So it's a very, very powerful way to reject a variety of noise. It's something you cannot do with WIMP dark matter, because WIMP dark matter is point-like interaction, right? So exactly. So there are a lot of ways to test this. So we think there are a variety of interesting directions in the future that can be pursued. For the QCD axion itself, one can, for example, think of a more optimal choice of polar crystal. We just use lead titanate because that's a number that we knew. Okay, it's quite reasonable that we can get factors of a few electric fields from some other sample. But we're still figuring that out. Definitely, samples of larger volume have the advantage that the magnetic field you can measure becomes better. All right, the bigger the thing, more flux you capture. Also, the magnetization noise goes down, so that's definitely a direction to win. Definitely longer T2. There's more, if these, we kind of took T2 to be about a second, but probably, 40 seconds is not unreasonable, as has already been demonstrated in silicon, for example. So that will also be a win for the highest values of F, right? Highest values of the PQ breaking scale. And finally, magnetometry. We showed numbers that were limited by SQUID magnetometers. There are magnetometers called atomic magnetometers or surf magnetometers. Those things are already do better than SQUIDs by a factor of 10. So in any part of the parameter space where we were limited by the magnetic, our ability to see the magnetic field, which is our dominant limit, if you use a different magnetometer, you can actually beat that down by how much ever you gain. So many interesting directions. So I'm almost about to shut up now soon. So every long story needs to have some morals. Here are my morals, or rather the morals of this story, not specifically my morals. The reason why this works at all is because I'm measuring the model-independent, non-derivative coupling of the axion. right? The coupling two gluons, which it must have. And because it's non-derivative and because it's a direct measurement of phase, there's a very, very moderate scaling with FA. Okay? It was a very powerful way to probe for a variety of axions or very large parameters of FA. Importantly, the signal is proportional to the square root of the dark matter density. Right? So if I make a factor of 10 improvement over all the numbers I talked to you earlier, I can search for a much smaller fraction of dark matter. So a factor of 10 buys me 1% of dark matter. Okay? Pretty easy to go in that direction. This works at all because I'm looking at a time-dependent signal, an AC signal. Okay? And that gives me two things. It gives me a resonant boost, so that I can build systems that dramatically enhance the value of the base thing I'm looking at. Plus it also helps me with sort of noise amelioration. I'm only interested in noise at a specific frequency as opposed to some long, thing that changes over days or something like that. Okay, very, very useful. And this is a point that I just mentioned earlier, which is that if you see a positive signal, right, in these experiments, it's very, very easy to do that signal verification because the signal will remain coherent over the axion wavelength, and at these values of f and these masses, that's a very, very long length scale. So it's very, very easy to measure and verify that what you're seeing is actually the axion and not some junk. One can scan over a very wide bandwidth by changing the magnetic field. Okay, that's pretty easy to do, right? External magnetic field. And very importantly, this is a scalable experiment. I can start small, I can understand the experiment, right? Understand the noise very well, see how to beat it, and then make it bigger and bigger. Okay. So in some ways, I think the situation is similar to the ideas that Goodman and Witten pioneered in the 80s, right? When they were looking at cross sections order 10 to the minus 38 centimeters squared for dark matter direct detection. And in the last 20 years, due to an enormous amount of very impressive work by experimentalists, we've probed 8 to 9 orders of magnitude. I mean, 8 orders of magnitude now with xenon 1 ton getting there, right? A lot of orders of magnitude have been probed in the parameter space. And the fundamental reason why this worked is because the technology they talked about, which was just this little detector and you're looking for something scattering, was a scalable thing. You could start small, understand it very well, and make it bigger and bigger. And that is very similar to the kinds of ideas that we've proposed. And we certainly think that axions deserve a similar effort. With that, I just want to conclude the final slide here, putting it all together. All the parameters of the axion set by this one scale FA, where that symmetry is broken. Below 10 to the 9, all ruled out. Above 10 to the 12, you can be dark matter. This is where the current ADMX cavity search experiments are. And these NMR style experiments that I talked about, these can most easily search for axions in kilohertz to megahertz. That's the frequency where they really like to be at. There are a lot of benefits, long coherence time, things like that, that make this a much easier parameter space for us to probe than lower values of FA or higher masses. Undoubtedly, the technological challenges. I'm not going to say everything is easy, but this seems like a pretty promising direction. Okay, thank you.
Surprisingly, you were on time.
Yeah.
Not by your standards, but by what we are used to, so we can even have you answer questions.
Answer questions, yeah.
So give us the time scale.
Time scale. So we're trying to raise money right now, and I don't know how long that will take. But we're thinking of a few years, 4 to 5 years. Would be so. There is depending on what you want to do, right? So if you're searching for the QCD axion specifically, we need R&D. We need to put all of this together in one crystal. This ferroelectric, all of that stuff needs to go together. So that will take some time. But if you're just interested in looking for a general axion-like particle, dark matter, that can happen relatively easily. All you need is cool down some liquid xenon, polarize it, and see if some spin is precessing. And it turns out that there's a group in Mainz where they happen to have some data. Okay, so they were looking for some spin precession.
Mainz?
In Germany. Mainz. So, in fact, they were looking for some other effect, whatever, but they happen to have data at sufficiently rapid timescales that we are now asking them to actually go through the data and see if they see a variation. So, what they've done is a very similar kind of experiment. They just have some spins aligned, and they're looking whether the spin changes, over a few second timescale, right? Now, they're not going to be good enough to see most of the axion parameter space, but they'll be a beginning to see if they see variations in that kind of data. So those things could happen much more quickly because that does not require this R&D for the QCD axion specifically. For the QCD axiom, we would have to put these things together. I don't know how long that takes. In terms of cost, we estimate on the order of a few
Because of
million.
the parameters being like blah blah blah. And you're saying what this mine's business that's just for some random action.
Yeah, random axiom, exactly. Yeah, like a random axiom that couples
In
to.
the sense that F can be different from what you need, and so.
No, it is this operator. Okay,
Right.
this d mu a or fa.
Sure.
Exactly. Yeah, precisely. Yeah. So
Just
there's
the
no.
biology may be more favorable.
That's right. Yeah, it is these guys somewhere here, right? Alpha dark matter.
Yes.
Because that's something where the Fa and M are not correlated anymore.
Yes.
So
Yes. Right.
exactly.
Must the QCD axion have this operator as well?
Well, it usually does. It does not have to.
What's the issue?
You can tune it away. I mean, a typical Goldstone boson will, this operator, it protects all the symmetries of the Goldstone boson. So you typically expect it to exist. So in most models it will. But of course, it's not like you can of course come up with some other contribution that exactly cancels it.
What do you mean by some other contribution?
Well, the coefficient can be made to go 0, right? Like this is coming because I'm integrating out some stuff in a loop, and if I choose exactly the right things that need to go in the loop, then probably I can cancel it.
But you can probably cancel it with one loop and then it comes back up.
Comes up exactly.
Yeah.
Exactly.
So basically it's that.
It's basically that. Yeah.
It's just that the coefficient numerical
Can be much
factor
smaller,
Can
exactly.
be somewhat smaller.
Exactly.
By the way, I mean, this business of starting, the setup of the experiment, I'm still a little bit confused about the geometry. So you take this external magnetic field that polarizes the magnetic spins, and therefore nuclear spins in some direction.
Yes.
Then you take orthogonal electric field,
Yes.
and if you didn't have EDN, then this would just sit there.
Exactly.
Now you have EDN that's turned on. Is it important that it's changing in time to
No.
get it to spin?
No.
So how does it?
So if you have a static EDM,
Yes.
it's actually easier to look at it directly from the formula.
Okay.
Okay. Right. Let's look at this formula here. Okay. So imagine it's a static EDM, constant in time.
What I'm trying to understand, just simple geometry. If you don't mind, can we ignore the formula and just explain from the arrangement of forces?
Yeah. So if it's static EDM, the spin, the dipole will precess.
As long as the EDM is not parallel with the external field.
Yes.
Right. I mean, or
Correct.
orthogonal. So some
Well,
general direction, right?
As long as the EDM is not parallel to the electric field,
Yes.
it will precess. Right? So, of course, like the EDM is along the direction of the spin.
Yes.
So, if I go to my previous thing, right? So, here I do this. No EDM, nothing happens. When you have an EDM, whether it's time varying or time independent, it will nevertheless start precessing. Right? Because there's an EDM perpendicular to an electric field.
I'm trying to remember, what is the force? Oh,
It's a torque.
QB cross
It's
B.
a torque, right? It's like.
It's QB cross B.
Yeah,
That's the point.
that's right. That's right.
That's the point.
Yes.
Sure.
Okay.
Can you say again why that, go back to the formula we were about to discuss.
Sure. Yeah.
Where does the factor in the denominator arise from?
So formally speaking, this is a two-level quantum system. Spin to the left, spin to the right. Right? They're split in energy by 2 mu b. Why is there a precession? There's a precession because the electric field is coupling those two spin states together. The EDM, the full coupling, D dot E, is coupling the electric fields, the two spin states together. So I'm quantum mechanically doing a mixing between the two levels, right? And that means there's an energy denominator, which is where this comes from.
But it's not possible to get anywhere near the singular point, I guess, experimentally.
Yes. So to get the singular point is basically like, that's the Q of the resonance or whatever. That's the standard way of talking about it, right? And
But MA is what, so very much smaller than to U and B?
No, MA and no. In fact, we want them to be very close.
Well, that's what I was asking.
Yeah.
So you can approach.
You can approach exactly. But it's limited by two things. It's limited by the coherence of the axion field, which is essentially spread by mv squared. So that's the most this denominator can ever be made small, because the axion is no longer a single frequency at a point. Beyond that, it's spread out.
So experimentally, would you, as you scan for different MA values, you would use different B values?
Yes. Yes.
And that's where you came up with this time scale, I forget how many seconds you could use.
Yeah, a few seconds, exactly. Good. Yes.
Okay.
Yes. Yeah.
All right.
So for every few seconds, you can exclude some parameters. There.
Exactly.
So, no further questions? Thanks, Surjeet, again.
All right, thank you very much.